Hi everyone, thanks for joining me today. We are going to be talking about isosceles and equilateral triangles. This is section 4.8 in your textbook. So during this video, we are going to be proving some theorems about isosceles triangles. We'll be discussing isosceles and equilateral triangles and doing some practice problems with those as well. So during the video, I'd like you to pause the video and complete the proofs and the practice problems, and then we will review the answers. In some cases, there are several ways to prove these theorems, and we'll talk about this. So your way may not be the same that I did it, and we can have a conversation about that. So the first thing that we have is the isosceles triangle theorem. Before we start to talk about that, let's just talk about what an isosceles triangle is. The definition of an isosceles triangle says that it's a triangle where at least two sides are congruent. The two sides that are congruent are referred to as legs. The angles that are opposite them are referred to as base angles, and this is the base. So you have two legs, a base angles. Angles B and C would be referred to as base angles. And then the angle that is opposite the base is referred to as the vertex angle. So here, when we take a look at the isosceles triangle theorem, it states that if two sides of a triangle are congruent, then the angles opposite the sides are congruent. So in this diagram, it's given that side AB is congruent to side AC. Our conclusion would be that angle B and angle C are congruent to one another. Now the converse of the isosceles triangle theorem, we refer to that as CITT, states that if the two base angles are congruent, so if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So in this diagram here, we have angle E is congruent to angle F. That would mean that the sides opposite them, so side DE and side DF, are congruent to one another. So the way in which we prove these theorems is we add an auxiliary line. And we have some guidelines on the way in which we are allowed to draw an auxiliary line. Remember, we can only give an auxiliary line one condition. So if I wanted to, I could draw an auxiliary line that bisects an angle. Or I could draw an auxiliary line that connects to the midpoint of a segment. I could draw a line that is perpendicular to another line. I could draw a line that's parallel to another line. But the bottom line is that I can only give this auxiliary line one condition. So as we take a look at proving the isosceles triangle theorem, ITT, the given information is that line segment AB is congruent to line segment AC. We're trying to prove that angle B is congruent to angle C. Add in an auxiliary line and give it a condition and see if you can prove that angle B is congruent to angle C, and come on back. Okay, so my strategy is to draw line segment AD that bisects angle A. And again, the reason that I can do that is that every angle has exactly one bisector. So if I draw it, I'm going to attempt to draw it straight down here. That's a terrible line, but here's my line segment AD. And I'm going to say that it bisects angle A. So step one of my proof is the given information. Step two is to construct line segment AD bisecting angle A. The next step, third step in my proof, would be to say angle BAD is congruent to angle CAD by definition of angle bisector. Step 4, AD is congruent to line segment AD by reflexive property of congruence. That gives me that the two triangles are congruent by SAS, and then therefore angle B is congruent to angle C by CPCTC. Now somebody else might have said to me, Manoogian, I constructed it so that it meets the midpoint of the opposite side. And I ended up getting that the three sides of the two triangles were congruent and proved that the two triangles are congruent by SSS. That's another way. So let's move on to the converse of the isosceles triangle theorem. Again, add in an auxiliary line and see if you can prove that angle E is congruent to, that line segment DE is congruent to line segment DF. The given information is that angle E is congruent to angle F. Put the video on pause and come on back. So I went with still the same thing that I said in the previous proof, that I'm going to draw line segment DG that bisects angle D. And so that gives me step 1 of the proof is angle E is congruent to angle F. Step 2 is construct line segment DG bisecting angle D. By every angle has exactly one bisector. The next step would be to say that angle EDG is congruent to FDG by definition of angle bisector. Next step, DG is congruent to DG by reflexive. The two triangles are congruent by AAS. And then that gives me that line segment DE is congruent to line segment DF by CPCTC. So I hope you got it. Now again, you could have drawn DG perpendicular to EF. You could have drawn DG so it connects to the midpoint of EF. If you did that, however, you wouldn't be able to prove the triangle's congruent with that if you had just the midpoint. So you'd have to have done it a different way, either perpendicular or an angle bisector. Interesting. Okay, so take a look at this problem, put the video on pause, tell me what you can come up with. So hopefully you see that you have two pairs of congruent sides. So ITT applies, and we end up getting that angle F is going to equal 79. Therefore, the angle is 79. In the next problem, again, we have two sides congruent, which means that the base angles are congruent. So we set this 3x equal to x plus 44. Everybody go ahead, solve for x, and find the measure of the angle. Come on back. Hopefully you found that x was 22 and the measure of the angle is 66. Okay, so now we have corollaries. A corollary is a baby theorem. It's an offspring of the main theorem. We had corollaries in previous sections. So here, if a triangle is equilateral, then it is equiangular. So that means that if all the sides are congruent, then all the angles are congruent. The next one states the opposite. If a triangle is equiangular, then it is equilateral. All the sides are congruent if all the angles are congruent. So taking a look at this diagram, we see that it is an equilateral triangle. Therefore, the measure of angle L would be what? See if you can figure out what the value of x is. Hopefully you have put the video on pause and figured the answer out. I ended up getting that x is equal to 14. Moving on to the next problem. Identify what kind of triangle we have. The side, I'm not sure if it's cut off, but line segment JL is 2t plus 1, and KL is 4t minus 8. Those sides would be congruent to one another. You need to solve for t and then find the length of JL. So t is equal to 4.5, and the measure of JL is 10. Okay, this next one deals with, example 5 deals with proving a segment drawn in an isosceles triangle at the midpoint of each of the sides that are congruent to one another is half the measure of the base. And we will actually be talking about this in the next chapter, but this gives us some justification of why it is indeed true. So we're going to do what's referred to as a coordinate proof. And here's the setup. If we draw it on a coordinate plane, if AC goes from 0, 0 to 4A, comma 0, what is the length of AC? I hope you all said 4A. Now, what I need to figure out is what would be the coordinates of point X and point Y. If they are the midpoints of each of the respective sides, you can use midpoint formula to figure out the coordinates of X and Y. So please go ahead and do that. I hope you found that X would be equal to A, comma B, and Y would be equal to 3A, comma B. So if I know that the length of AC is equal to 4A, how can I prove that the length of XY is equal to 2A? Well, we'd have to use the distance formula. So everybody go ahead and do that and see what you can come out with. So XY is equal to 2A, so therefore it is half the length of AC. The next one is asking us to prove that XYZ is isosceles. So how would we go about doing that? In this diagram. So everybody give your thoughts, jot something down, see if you can figure it out. What would be the coordinate of X? Again, if it's the midpoint of line segment AB, what would be the coordinate of Y and what would be the coordinate of Z? Again, use midpoint formula to figure those out. So XZ and YZ both equal the square root of A squared plus B squared. So indeed, triangle XYZ is isosceles. So here's some problems to wrap up the section. Put the video on pause and solve these problems. For number 1, I hope you set up the two equations equal to one another. And X is going to equal 9, and the measure of angle R is equal to 28. For number 2, to find the measure of angle P, that's the vertex angle, so you have to do some work for question number 1. Figuring out that the measure of angle R is 28, the measure of angle Q would be 28, so subtract the sum of those two from 180 to get the measure of angle P, and you're going to find that it is equal to, hopefully, y'all got 124. Now for question number 3, there really isn't a lot of work that's involved here. Hopefully, if you recognize that this triangle here is isosceles, if this is 52, then this is 52. And this angle is a remote exterior angle that is equal to the sum of these two angles. So 52 is equal to 2x. So therefore, x is equal to 26. So I hope you all did well. I'll catch you later.